So we focused on determining or showing how you can measure molar, the partial molar volume and the partial molar enthalpy for mixtures. But here I want to kind of focus a little bit more on how you determine the partial molar Gibbs energy, or the chemical potential of a species in a mixture. To set the groundwork for this, what we need to recall is that from our fundamental relations for the Gibbs energy, we know that dg, dp, at constant temperature and some constant species, is equal to v. Okay. If we then took the partial derivative of dg, dp, took another partial derivative of it with respect to d and I, to have this constant p, t, and I, what we would be having is this p, t, and j is not equal to I. But we know that the partial molar partial derivative of a volume with respect to species Ni, by definition, that is just this, the partial molar volume of the species in the mixture. On the left-hand side here, though, what we could do is we could play around with our commutative properties of the mixed double partial derivatives. So we could rewrite this left-hand side like this. This is all at t and I. And so that would give us that d here, we have dg, d and I, and that is the partial molar Gibbs energy, or the chemical potential. Okay, and so what we get is that the partial derivative of the chemical potential with respect to pressure is going to be equal to our partial molar volume for that species. And so what this equation is telling us is that if VI bar is known, we could then just figure out how the chemical potential of a species in the mixture, how that changes as a function of pressure. Okay, and you could determine how that changes by integrating that above equation. Okay. All right. So that's how we could get the pressure dependence, and we see that it's related to the partial molar volume. Let's now look at the temperature dependence. Okay. So from chapter 7, we saw this relationship for Gibbs energy. Okay, we saw that the derivative of g over t is equal to negative h over t squared. Let's now take the partial derivative of both sides with respect to Ni. P Ni, P T, j is not equal to I. And that's going to be equal to negative d and I h over t squared, constant p, t, j is not equal to I. Okay? And we know, at least since here we're taking the derivative with respect to Ni, so we could pull out that t squared. So what we would have is dh over dni, and by definition that is the partial molar volume, or partial molar enthalpy. Okay. On the left-hand side here, once again, we could apply the commutative property for mixed double partial derivatives and switch these two. Okay. And doing so, once again, this is that constant T, so we could pull that out, and we would get dG over dNi, which is just the chemical potential. Okay? Alright, and so what we have is d mu I divided by T dt at constant P and I is equal to negative HI over T squared. Okay. And so just like we saw with molar volume, if we know the molar, or the partial molar enthalpy, if those are known, whether we do it graphically or we do it through an analytical method, we could see how temperature affects the chemical potential by just integrating this equation. And I also want to point out that this partial molar enthalpy, one way you could think of it is it's similar to the latent enthalpies we talked about for pure substances. So when we talked about, delta H of vaporization, delta H of melting, here this would be looking at the differences in partial molar enthalpies of a species as it went from the pure species to the mixture. So that's at least the sort of physical understanding behind it.